Hello, everyone. Thank you for attending our session. We will speak about Apache Iceberg and Delta tables with serverless Spark. So we're Nicole Manjunta and Franklin White. We're both strategic cloud engineers at Google. This is our agenda for today. So let's get started. We'll start by talking about table formats. Apache Iceberg and Delta tables are both what we call table formats. And this is basically they're a way to bring database-like features to your data lake. So what do I mean by database-like features? I mean functionalities such as ACID transactions, data versioning, time traveling in your data, schema enforcement, schema evolution, and so on. So this is the kind of functionalities you get from table formats. And furthermore, with Dataproc Serverless, these features can be leveraged without having to create, manage, or clean up a cluster. So now let's talk about a little bit more in detail of Delta tables. So the key component to understanding Delta tables are the transaction logs. That's where the magic happens. So these transaction logs keep track of every change, every operation over your data lake. This allows you to have a single source of truth. It also allows for data versioning. And since transaction logs are only written for complete operations, you also get atomicity. To better understand how this works, please focus on the illustration on the right. So if you write files to your data lake, this gets recorded in a JSON file, which is the actual transaction log. And if you then want to remove those files and add a new one, that operation is also recorded in the transaction logs. What happens here is that you're actually not removing the original files, you're just marking them as removed within the transaction log. So we can go into a little bit more detail over that in this demo. Okay, let's see Delta tables in action with serverless Spark. This is the command we use to submit a PySpark. It's a pretty straightforward command. So basically no cluster has been created, no cluster needs to be created. It's completely serverless. Please note that we are passing among the arguments the jar with the binaries for Delta Core, which is the basic Delta functionalities. We're also specifying a container image. This is something particular for the use case. Since we are submitting a PySpark code, the way Dataproc Serverless manages Spark dependencies is with a custom image. So that's why we're passing this here. Let me give you a quick glimpse of the Docker file for that image. It's pretty straightforward, standard stuff. Please pay close attention to this line. It's basically the reason we're using custom image is to install Delta Spark in our environment, which is the Spark library used by Delta tables to used by PySpark to interface with Delta tables. So basically, it's a library used by Python to actually read, write, time travel, and so on, Delta tables. So this is used by our code, which I am going to show you now. So in our code, what we're trying to do is that we're trying to simulate a simplistic version of a data lake to which data is constantly written, and then data is overwritten for some reason or another. And this is a common use case or common scenario, in my opinion. You can have a data lake to which several processes, several ETLs, several streams are constantly writing data, appending data. And then for some reason or another, you might want to delete or overwrite existing data. That's what we're trying to simulate here. So the first two steps, we write data, we append data, and then finally overwrite data. And usually what happens here in the standard data lake is that when you overwrite the existing data, the previous files get deleted, and those files are no longer available. But with Delta tables, that's not the case. With Delta tables, the files are kept, but are marked in the transaction logs as removed. And that's what happens here. And that enables us to actually time travel the data as seen in line 32. We are reading out our Delta table for version as of 0. That means we are going back in time and getting the original version of the data. And this is one of the main functionalities of Delta tables. You have the transaction logs as a single source of truth that allow you to go back and forth to different versions of your data, in case anything goes wrong, in case you want to check what happened, and so on. So here we see the output of our job. Let's wait for it to finish printing, but we can start seeing we can start seeing that we are getting logs of different versions of our data lake. So let's go through them in detail. We have version 0, the original version, just some records written to our data lake. Then we have version 1, the original records plus some additional records that got appended. And then we have version 2. Version 2 is the current, it's the actual version of our data lake. As you see, the records from previous versions, version 0 and 1 got removed. We're only seeing the records of version 2. So now what we did is that we time traveled and got the original version, version 0. That's the final log there. And you can see that the records of that last log are the same as the records of the original version. So we successfully recovered data from a specific point in time, a specific version of our data lake thanks to Delta tables. And let me show you how this happens, what's going under the hood. So I'm going to give you a quick glimpse of the most recent transaction log so we can see in more detail how Delta tables achieve these functionalities. Here, the interesting part is the remove lines. So this removes basically what's going on here is that the files from version 0 and version 1 of our data lake are being marked for removal. The actual files are not deleted from the storage. They're just marked as removed. That way, we know what's in the current version and we know what files were added or removed at every version at every point in time. And this allows us to go back and forth and actually do disaster recovery, error recovery, and gives us more traceability. So once again, this is a command. This is how we ran our PySpark PySpark code that leverage data table functionalities. It's a very straightforward command, and once again, we run it without having to create any cluster, without having to manage any cluster. And now that we're done, there's no cleanup to be performed. We're basically done with the code. So that's it for the demo. And now my colleague Nikhil will talk to you more about Apache Iceberg.
Thank you so much, Frank. So now let's take a deeper look at Apache Iceberg. So Iceberg is an open table format that solves a lot of consistency problems that is typical of existing metadata catalogs like Hive. It does this by essentially creating an abstraction layer between the table structure and the underlying physical data. Iceberg tracks and manages all the file changes to a table over time, and this enables transactional consistency with isolated writes and reads. This helps with schema evolution, time travel, version history rollback, and also partition layout evolution based on queries and data volume. Also, while querying tables, Iceberg does not require expensive directory listings. Because it already has all the metadata tracked, it can enable advanced planning and filtering capabilities for high query performance over large data sets. Now let's take a quick look at the architecture of Iceberg and see how it achieves all these benefits. There are essentially three layers in the architecture of an Iceberg table: the Iceberg catalog, the metadata layer, and the data layer. The catalog is the central place which stores the current metadata pointer for Iceberg tables. Iceberg supports having Hive Metastore or Hadoop Warehouse as catalog, or if you want, you can also add Iceberg support to Spark's built-in catalog. For example, in this diagram, there are two metadata files, and the value for table's current metadata pointer is the location of the metadata file on the right. Next up is the metadata layer, and this contains metadata files, manifest lists, and the manifest files. As the name implies, the metadata files store the metadata about a table, and this includes information about the table schema, partition information, snapshots, and which snapshot is the current one. The manifest list, aptly named, is a list of manifest files. It stores the location of a manifest file, the snapshot information, partitions it belongs to, and the lower and upper bounds of partition columns for the data files that it tracks. Finally, the manifest file is the one that actually tracks a subset of data files in the physical layer, and it stores statistics about each file. These statistics are helpful for efficient query planning. The last layer, data layer, it basically consists of the physical data files. With that basic understanding of Iceberg's architecture, let's take a look at how to build and query Iceberg tables on GCP using serverless Spark. Here, we navigate to Dataproc, serverless, and batches. This is where we can see the submitted batch jobs and the relevant information on the console. Jumping over to the Spark code, first thing we need to create is a new Iceberg Spark catalog. In this case, I'm naming it as local. And as stated earlier, this can be either Hive Metastore or Hadoop Warehouse. For this use case, I'm creating a Hadoop Warehouse type catalog. I'm also setting my warehouse directory to a GCS path that I've already created. This warehouse directory is where the Iceberg tables will store the data and the metadata files once we create the table. Next up, let's create a table called students in a database called DB within the local catalog that we just now created. And we are writing 3 records into this table. Let's go ahead and perform some more additional operations on it. So altering the table, I'm adding a new column called grade and inserting 2 more records. We then read all the records that we wrote to the students table into a Spark data frame and print it out to the console. Iceberg also allows us to perform table inspection by providing support for metadata tables. Here, we are able to query the table's history and the table snapshots. To build the jar, I have added the required dependencies for Spark and Iceberg Spark 3 runtime to the build SPT file and packaging it. Once the jar is generated, let me push this jar onto a GCS bucket, which I will be referring at the time of job submission. So in order to submit a serverless batch, we submit it like a typical Dataproc submit, but instead of using gcloud Dataproc job submit, we use gcloud Dataproc batches submit and pass the required job parameters. Here, I'm passing the location where the job should run, my main class, my runtime package dependencies, and the path to my jar file. So once I submit my job, let's jump over to the console and see that our job is submitted successfully. While the job is running, we can also see the information we provided at the time of job submission, and also the driver and executor course that have been assigned for my specific execution. Once the job completes, we can view the output either in this console or from the gcloud CLI where we submitted the job. The job is now completed and we are able to see all the records from students table that we wrote to it. Along with this, we are also able to see the revision history from the history table and the associated snapshots for each commit performed on the students table. The snapshot table has the snapshot ID, the operation performed, and the corresponding manifest list file path for each snapshot. And because we perform 2 operations, 2 separate inserts, there are 2 snapshots that have been created. And because Iceberg supports time travel, let's take a look at the table state during the first snapshot. Here I have another job which takes the snapshot ID as the parameter and fetches the table state for that specific snapshot. Let's submit this job in a similar way to how we submitted earlier. And here, let me pass the snapshot ID that I copied as a parameter. So we can see that the job is submitted. Let's jump over to the console and see the current state. So in this case, note that the table only shows the 3 records that we inserted as part of the first commit. In this way, we can time travel and even restore the table to a specific version. Also, let's take a look at the files in the warehouse directory. So we have our table path created in the bucket, which houses the data files and the metadata files. The data folder contains the actual Parquet files of the records written to table. And the metadata folder contains the metadata files. So here, if we note the version history, this is what points to the latest version of the metadata file. So in this case, it's version 4. The snapshot files are nothing but manifest lists which point to specific manifest files. And those manifest files keep track of the actual data files in the data folder. This is how Iceberg is able to keep track of all the changes that is being done on a table. That brings us to the end of our presentation. So we took a look at some of the salient features of data tables, delta tables, and Apache Iceberg, and how easy it is to build and submit serverless Spark jobs without the need to manage any clusters. Thank you for listening to us, and feel free to reach out with any questions. Thank you.